So let's look back on all the different sorting algorithms that we have considered. So one of the important criteria that we should not forget is that sorting often happens in phases, right? So we might have a list of names of people, say Ashwin, Bharati, Chandar, and Deepa, right? So we have sorted this in order, and they might have got some marks in an exam. So they maybe got 60, 43, 60, and 95. Now we might want to sort this by marks. So when we sort this by marks, of course we need to exchange the position of Bharati and Ashwin, but we don't want to exchange the position of Ashwin and Chandar. So in other words, we don't want to disturb the sorting of alphabetical order. So the final answer should be Bharati has 43, Ashwin has 60, Chandar has 60, and Deepa has 95. Okay, but it would be wrong if we said Chandar and then Ashwin. Not wrong, but undesirable. Right? So if we have a list of students in alphabetical order and then we sort by marks, we would expect that those with equal marks are still sorted in alphabetical order. So in a spreadsheet where we have a kind of a table with columns, so supposing we sort by this column and then we sort by this column, okay, the second sorting should not disturb the order of the first sorting. So this is called stable sorting. That is, if there was, so very often when you're sorting on one attribute, but there may be other attributes. So a data item is not typically a unique value. It's not just a number, but it's a, so you're taking names, marks, and various other things, address, maybe phone number, and you might sort on different. So think of a spreadsheet where you might sort on different columns. So each successive sort should not disturb the previous sort. So this is called stable sorting. So this is obviously desirable because we do it all the time, and we really would be very unhappy if the next round of sorting disturbed our first round of sorting. So which of our algorithms is stable? So quicksort, as shown, is not a stable operation. So remember that we took the pivot, right? And in the, at least in our implementation, what we did was we constructed this lower set and then this upper set to the right of it. So, right, so this is the picture we had, and then finally, and this is the crucial point, we do this swap. So imagine that we have a situation where here we had, for example, at this point Ashwin with 60 marks and Chandar with also with 60 marks, right? So at the point of constructing the lower set, they were in the correct order as in the original input. But now after swapping, what happens is that the pivot has come here and Chandar with 60 marks has gone here, right? So this swapping operation has basically reversed the order of A and C with respect to what it was in the input, and henceforth, therefore, this order will get jumbled. So the swap operation during partitioning disturbs the original order, right? And this also happens in things like selection sort, because in selection sort, wherever we do this long distance thing, so remember in selection sort we pick the minimum and then we exchange it at the beginning. Now if the element at the beginning had the same alphabetical order as, I mean it's smaller in the second one, now it moves to a later point in the array and the order gets disturbed. So any kind of long distance swapping is very dangerous for stability. What about merge sort? Well, merge sort would normally be stable provided all we want is that something to the right should not go to the left of something in the original array. So we don't want if we have two elements here and here which should remain in this order, we don't want them to be exchanged. Now why would they be exchanged? They would be exchanged only if they were equal, right? That's the only case where stability gets destroyed, where equal elements are disturbed with respect to their previous sorting. So we have to make sure that no element from the right comes to an element to the left of something from the earlier array. And when we are merging, basically that's why we said that in the case AI is less than or equal to BJ, we pick from A, and only, so if we had made the mistake of writing less than and then we use greater than equal to select from B, then when they're equal we would first pick from B and not from A, and that would create instability, right? So crucial in our merge operation is that when AI is less than or equal to BJ, we pick the element from A in preference to B. So this preserves the left-right order of equal elements with respect to the original order, and since merge sort, as we have done, is stable. You can also check that similarly if you do insertion sort carefully, then insertion sort is also stable. Now this is not to say that quicksort cannot be made stable, it's just that the way we have implemented it, quicksort is not stable. Another criterion which is related to what we just saw is that we have only concentrated on the number of steps required in order to compare and exchange two elements. But you might want to do other things. For instance, you might want to penalize movements which take you across large segments of the array. So you might want to say that it is not so good to exchange things far away, it's better to exchange things near each other. So something like bubble sort, which we didn't look at, which only exchange adjacent elements, would be better than something like selection sort, which exchange across large intervals. Now, this could happen if data has a cost, and supposing you're sorting an array, but this array is across different, it's so big that it's not stored on a single server, then each time you want to swap from one server to another, you could pay an extra cost which is different, right? So in other words, there might be different criteria which are behind the scenes which we don't see. Okay, so imagine when you're sorting something by hand, supposing you're sorting a bunch of heavy cartons, then you can imagine that moving a heavy carton a long distance is more expensive than moving it a short distance. Right? So there could be other criteria which govern your cost of sorting, which we have not considered at all in this, and people have looked at these things in the literature. So very often the question is asked, which sort is best? Okay. So unfortunately, it turns out that no single sorting algorithm is always guaranteed to be the best. It really depends, as we said, like sorting in terms of movement and other criteria. Some sorting algorithms may work well in some contexts, some in another context. In most memory-based contexts for simple arrays, quicksort is the best. And this is why, as we said, quicksort is usually the default implementation of choice for built-in sorting algorithms, provided we do something intelligent about choosing the pivot and various other things. On the other hand, when we have to move a lot of data, sometimes we cannot store the entire thing. If we are sorting a database, we cannot sort the entire thing in the memory. So actually we use a variation of merge sort, which is called external merge sort. So it really depends on the context. Sometimes you use one, sometimes you use another. If there were a best algorithm, there would be no need to study the other algorithm. So the very fact that many of these algorithms are studied shows that in different contexts you might need to use one or the other idea in order to make things work better. Right? We have seen merge sort as an order n log n algorithm. There are other n log n algorithms. We will see one later on in this course called heap sort. The main thing to remember is that if we have a naive n squared algorithm, which is not like quicksort, provably n log n in the average case, then this will only work for small data. However, sometimes for small data, the simplicity of a naive algorithm beats the complexity of a complicated algorithm. So you could even have hybrid algorithms, right? You might use divide and conquer when n is large, and then when n becomes small, then you switch over to maybe insertion sort. Okay? So there are many different strategies that people use, and very often experimentally they arrive at some combination of strategies. So it's not enough to say that one algorithm is the best. You need to have a good idea about what works and what doesn't work so that you can tailor your sorting procedure to suit your requirement.